This is the fixed law equation for steady state in the binary mixture of A and B. So we're going to discuss on these two formula. One is in terms of concentration, the other one will be in terms of partial pressure. Okay, so this is the molar flux for a binary mixture of A and B, which is given in the terms of a partial, in the terms of mole fraction, in the terms of mole fraction. And you should know that the mole fraction of A, which is XA, should always equal to the concentration of A over the total concentration in the mixture. And where C, or the total concentration of the mixture, is given by the concentration of A plus the concentration of B. Okay, so by having this formula, okay, so you're going to substitute the terms into the first equation, okay, and then you're going to get the following equation. Okay, so where your total concentration will be cancelled off with the existence of this term, okay, and leave you with the terms of concentration of A in the formula. But you cannot just use this formula in your calculation because you need to solve for the derivative before you can proceed with the substitution. Okay, so to get rid of this derivative, what you need to do is to integrate the terms. So you're going to integrate the derivative of concentration, and you're going to integrate the derivative of the distance of your flux. Okay, so when you introduce the derivative, in order for you to calculate, you need to introduce the lower limits and the upper limits of the integration. Okay, so the value for 1 represent at position 1, the value for subscript 2 represent the position 2. So same thing for the concentration. Okay, so it begin from position 1, it move from position 1 to position 2. Okay, so the concentration also represent the concentration at position 1 to position 2. Okay, but from the definition that we have learned regarding to the mass transfer, the diffusion or the mass transfer motion is from higher concentration to lower concentration. So you can see that your CA1 has a bigger value compared to CA2. Same thing with the distance of at position 1 is so when you talk about position 1 is lower value compared to position 2, but the concentration for position 1 is higher compared to position 2 to allow diffusion to occur. Okay, so you solve your integrals. Okay, you get the first term, which is CA2 minus CA1, and then you get for the Z, you have Z2 minus Z1. So your Z must be in meter. Okay, and the unit for concentration depends on the diffusivity, okay, or maybe depends on your constant or gas constant. Okay, so once you have this formula, okay, take a look here, you have negative sign, but here no negative sign. So if you look at this value, CA2 minus CA1, you get negative figure. So the negative figure will cancel off with this in front negative figure, so that you get this particular formula. Okay, so from this formula, you're going to use the given terms on the top of the equation to get the term in terms of partial pressure. Okay, so this is what you have to do next. So figure out how these concentration terms can be derived into the partial pressure terms. Okay, alright, thank you. It's your turn to derive the formula.